So can you see my screen now?
Yes.
Yes. Okay.
Yes.
Thank you. Good. So this is the representation space, and so what? Let me give you one more example. Actually, we'll be interested in this example. So let Q be delta n, the equivariated type A and quiver. Cyclic quiver on n vertices. And then I consider the module which I denote by U I n. So what's that? So let me denote the set of vertices. So they are just in bijection with Zn. So Zn just the numbers from 1 up to n. And then we have arrows from I to I plus 1. Oh, so the I would be fixed. So we have arrows from A to A plus 1. And then for UIN, so we have UIN upper A is C for any A. And the maps M from A to A plus 1. This is either 0 if A is I, or identity if A is not I. Okay, so this is my module. So let me draw a picture. So this n is 5, and then we have 1, 2, 3, 4, 5. And so I want to draw U 3, 5, and this is such a presentation. So I have everywhere one-dimensional space.
So, Evgeny?
Yes.
Could I think I cannot see what you wrote on the shared screen.
Oh,
Me too. I also have problem. I
Oh.
see on.
Oh, okay. Let's try to fix it. Okay. Can you see the screen now?
Yes.
Perfect.
Yeah.
Misha, can you see me?
Yes.
Okay, so this is so we are constructing a representation, and this once again UIN is one-dimensional at all vertices. So it all this is C, and then the maps are either identities or 0 at one place. So totally we have dimension 5, but well, the maps somehow depend on this I. So let me make a full screen. Okay, I hope it works now. Does it work? Good. Okay, so that's it. And now, so let me, maybe I'll get back to this general picture of representation, but let me move a bit further to introduce quiver Grassmannians. So, well, you can somehow give a very concrete definition. So let us fix and the Q module. So we just fix a representation of our quiver, and then let E be a collection of non-negative integers. So I from 0, and then let's assume that EI less than or equal to the dimension of MI. And then by definition, this quiver Grassmannian E of M is a collection of subspaces V A from M upper A such that the dimension of V upper A, is EA, and if we have we have an error from A to B, if we apply it to VA, then the result should be VB. So it means that this is the collection of subspaces in in each space corresponding to our representation, and they have to be compatible with the maps corresponding to the arrows. So this is the kind of set theoretical definition. Of course, if you want to make it into algebraic variety, you have to do something, but that's it, more or less. Okay, so now let me give you some examples. So maybe the most natural example is Q being the A1 quiver, and then M is just n-dimensional vector space, and E is some number less or equal than n. Then our quiver Grassmannian E of M is nothing but just the usual Grassmannian K of Cn. Because we have no arrows, it's kind of not too interesting. So another example is vectorizing. U is an equivariated, and M is nothing but Cn to Cn, actually Cn plus 1 better. Yes, so we have all the vector spaces are n plus 1 dimensional, and the maps between these are identity maps. And then E should be 1 to up to n. And then the corresponding quiver Grassmannian is variety. And so n plus 1 won't be. But in principle, the quiver Grassmannians are not that nice. So, for example, you will have U-A2, and the dimension M, dimension 2, 2. The representation looks as follows. So we have two-dimensional vector space here and the two-dimensional vector space here. So these are just basis vectors, and then the maps are something like this. So this one vector is mapped here, and the other vector is mapped to 0. And then I want E to be 1, 1. So I'm looking at one-dimensional space with these two dimensions. So the map is 1, 0, 0, 0. So this map corresponds to. So our A2 quiver is like this. So this is the quiver view, and this is the module M. Yes, so this is clear what was the picture. Yes. So these are kind of not to be confused. This is the quiver itself, and this is the module, picture for the module. And then E is 1, 1. So we are looking at one-dimensional space here. And the one-dimensional space here is actually this one-dimensional is mapped to this one-dimensional. And actually, this is so this quiver Grassmannian E M is reducible, so it looks like two copies of P1. Intersect at one point. Well, it's actually clear because so you can see that we want to fix one-dimensional space here. So if your one-dimensional space is this point, then you can choose whatever you want here. And this gives you one P1. But if your vector space here is not this one, but something else, then this component is fixed. And this is another P1, because here you can choose whatever you want. So, and they intersect by, the intersection is a point where you choose this one-dimensional space and this one-dimensional space. So actually this is this one. Okay. Good. So, and maybe even worse, the variety can be the quiver Grassmannian can be disjoint. So, for example, maybe the last example. Is say the quiver Q, what is called the Kronecker quiver. So two vertices and two arrows between these vertices. So this is called Kronecker quiver. And then you can have now M is C2, and the two maps are the identity map and 1 lambda 0 0. So you have two maps between two-dimensional spaces. One might be just identity, and another is something more complicated, though not very complicated. And then the Grassmannian 1 1 of this M is actually 2 points. Disjoint union of 2 points. So it can be easily seen that the 2 points correspond just to basis vectors in which this matrix is free. So, well, the kind of outcome is that more or less everything can happen, and there are theorems by Reinecke and also by Ringe, saying that more or less every variety can be realized as quiver Grassmannian. So no point to consider them in general, but there are many nice examples, and then you can somehow study these examples. Okay, so let me now switch from the kind of general stuff to the concrete definition to introduce the main player, and then I might get back to some general words later. So let's consider a very concrete example, Q being delta n. So this is the cyclic quiver on n vertices. And then my M is the direct sum I from 1 to n, UIN. So you remember this UIN is a representation of my quiver, which has one-dimensional space at every vertex, and all the maps are identities, but the one place where it's 0. So let me maybe give you an example. So example. Yes, also we use the notation U n for this representation. So if n is 3, then I have, let me draw this representation. So maybe I should say from the very beginning that the dimension of U over n is n and n at every vertex. So, because the dimension of each of the summon is 1, 1, 1, 1. So the dimension here is n, 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 n. And if n is 3, then here is the picture. Again, I have 3 basis vectors.
And it's the same in both places.
Yes, yes. It's important that n, the number of vertices is exactly the dimension of this representation. So here is the picture. So let me draw and then I'll explain. Here. Oops, what did I do? And finally, so say this is vertex 1, this is vertex 2, and this is vertex 3. So we have 3-dimensional spaces corresponding to each vertex. So this is one 3-dimensional space, this is another 3-dimensional space, and this is yet one more. Okay, and these are the maps between these 3-dimensional spaces. So you can see that so we have the rank of each map is 2. So we have 1-dimensional kernel at each vertex, and the representation looks like this. So this is an example, and so this is my representation, and the main
Show the general formula again for the
what?
For the maps.
For UIN or for
For the maps.
But so you see, this M is a direct map, direct sum of UINs. So if you know what is the UIN, then you know what are the maps.
Oh, the UIN are n-dimensional.
No, totally it's n-dimensional. So let me maybe write it once again that UIN. Totally, yes, totally it's n-dimensional, but it's 1-dimensional at each vertex. So you have your I.
Each vertex is a base.
Yes. So this is the picture for UIN. Yes, so at each vertex you have 1-dimensional, and this almost the whole cycle, but there is one gap. I map maps to 0. And then you see, for example, this you can find the U1, 3 here. So starting from this vertex.
Yeah, I was confused. I was thinking that the UIN are the components of the module corresponding to the vertices of the quiver.
No. These are sub-representations.
It's a different.
Right, right. So this is the sub-representation. For example, if you take UIN and take NJ, so the dimension of this is 1. And then this means that totally the dimension of this direct sum at each vertex J is 10. Right?
Which of them is UI U1 and which is U2?
Yes. So, for example, let me draw for you U1n.
Where's one?
So this green is U1.
Why is it one? Where is the one?
You see this one, this vertex 1,
Yes.
and this vertex 2, and this vertex 3.
Oh, it's the one that ends in.
Right, absolutely. Yes. So UIN ends at I. So you can see it here. Okay. So this is my representation. Now, by definition, so I introduce X, K, N to be quiver Grassmannian. Let me K here of this UN. Okay, so I take NK less than N, and then I take inside this representation, I take all these sub-representations. Yeah, by the way, maybe I should have said that mark. A sub-representation. So let me put it like so. Quiver Grassmannian, any quiver Grassmannian this is actually a variety of sub-representations. So maybe I put here Grassmannian E M. This is a variety of sub-representations of M of dimension E. Okay, so the condition I wrote was exactly the condition on sub-representations of a given representation. Yes, so the compatibility with the maps. So, well, this is just the definition of sub-representation. So what's written here is that you take sub-representations of dimension k, everything. So let me give you an example, and then we'll see how this is related to the last time story, to the last week story. But let me start with an example. So the simplest example is n equals 2, k being 1, and then so let me draw the representation itself. So here is my module. So I take a two-dimensional space, C2, and then another two-dimensional space, and then there are two maps. So since I have delta 2, so I have two vertices, and then maps from 1 to 2 and map from 2 to 1. And since I have two-dimensional spaces, well, I have two maps, and well, I can draw them very explicitly. So one map is somehow in this direction. It maps vector to another vector and this vector to 0. In an opposite direction, the map goes like this. So the two matrices, they are of the form 0, 0, 1, 0. And here this is 1, 0, 0. So one, maybe not draw them here, but rather I write them here. Okay, so I have two maps between the two-dimensional vector spaces, and these are the matrices corresponding to these maps. And then, well, I can ask what is the Grassmannian 1, 1 of G2. And this again very similar to what we've seen at the example of today. So we have to choose a one-dimensional subspace in this two-dimensional vector space, and there are two options. So the first option is that this is this vector, which is sent to 0 here. And then there are no conditions of this vector. And this is your P1, because if this vector is chosen, then the map backwards somehow sends anything to this very vector. So it means that you have something here and anything here, this is the P1. And similarly, you have another P1. So this is this picture. So, well, we'll have to remember this when we connect it to the totally non-negative Grassmannians. But just, well, here it's very explicit, and this is what you can somehow get here. So, well, this is something. And why do we care here? So let us make the first observation. So so recall that UN is the direct sum of UIN, I from 1 to n. And let me write, so this let E sub A E sub I upper A. So this is the basis vector of E of UIN upper A. So this is what Igor asked. So let me take this representation UIN, and let us take the one-dimensional space supported at vertex A. Okay, so this is my notation for the space of representation corresponding to the eighth vertex. So it's one-dimensional space, and let me fix such a basis vector. Okay, so then I can say that. So in my representation, EIA is mapped to either EI plus 1 A. Sorry. if A is not I, and so 0 if A is I. Okay, so what's happening here?
You sure you don't want +1 here?
Where?
Here, it's I.
This is I, yes, because you see, the I here corresponds to the summand UIN. So this is a sub-representation. Therefore, we never switch I to something else when we consider the map in our representation, right? So this is sub-representation. Therefore, the I should be kept.
It wasn't really clear from the previous picture for n equals to 3 that so here, there, that's what I think that's what I'm confused.
Yes.
Sometimes it looks like the number is not preserved. Like,
No, this is the kind of how to say. So this.
see, yeah, it is not always clear what the numeration is in each of them.
So if you wish, this is the jogging pattern like enumeration, and what's below is the Grassmann necklace type enumeration.
Okay, yeah,
So the way how you label the basis vectors is up to you, yes, but these are two different ways to label.
okay.
Actually, I will make a comment here. Да. Вот на той картинке, да? So you can see that we have this direct sum here, right? So it means that you take. Наверное, на складывается, да? Здесь тут 3 штуки. Окей. So this is my basis, and this A means that I somehow go from the 8th vertex to the A plus 3rd vertex. So now let me consider let us consider the so-called T fixed points. In the quiver Grassmannian K UN. So this K is KKK. So these T fixed points are actually nothing but, so as we have to choose the A in UN upper A, yes, for every A. So dimension of VA should be okay. But we say that VA should be the span of some vectors of the form E upper AI, where I is from IA, IA being a subset of the set 120. Yeah, so we take not an arbitrary point in my quiver Grassmannian, but only those points which are spans of basis vectors. And this IA, of course, has to be a subset of cardinality K. So we take cardinality K subspace, well, dimension K subspace, and to fix this subspace, we simply take a subset of cardinality K and inside this set from 1 to n. Okay. So that's it. But why do we want this? So let me write it as a condition. Which says that such a point, so VA being the span of
This P has dimension n squared, right?
say again?
P has dimension n squared.
The torus n minus squared.
Oh,
Well, it depends on
yes.
what t you
It
consider.
acts in its n dimension n, and it's acts in the same way on all the components.
Yes. It's acts on the same way. How to say at each vertex.
Yeah,
Yes.
in each-
Yes. Well, actually, this is the question is a good question. So I mean, actually, there is a larger torus acting on. No. So I mean, n squared is a torus acting on the whole thing,
Yeah.
but you wanted to preserve your Grassmannian.
Okay.
And this is some condition actually fixing it to that 2n dimensional torus. But so far we are doing a very naive thing. We are just considering a torus acting the same way at each.
Okay. All right. Okay.
So this defines point in our Q Grassmannian n if and only if this collection is Grassmannians. So, and actually, well, this is easily seen because of what's the condition? The condition is that, so let me show you once again the map. So you see the map says that EIA has to be mapped to EIA plus 1 or to 0. So it means that, and we want our point to be compatible with the maps, meaning that if you have a vector EIA at the 8th vertex, then you have a vector EIA plus 1 at the A plus 1st vertex. So in terms of the sets I, so the proof is actually, the condition is that so if we have I in IA and I is not A, then we conclude that I is in IA plus 1. Oops. What am I doing wrong?
Do you want
To erase. So if I have I from IA and then I is not A, then I is from A plus 1. Is this exactly the definition of the Grassmann necklace? And actually, let me give you a remark. And thanks to Igor for pointing this out, that there is this juggling patterns of Knudsen, Lam, and Speyer.
I think they were actually defined just by some, in the rank. So
Yes, please. So these juggling patterns, they are, I gave a wrong definition last time. Let me correct. So the correction is as follows. So, well, the definition of the Grassmann necklace is given here, and here you have J1 up to Jn, and the condition is that if J is from Ja, so again the Ja are subsets in 1 to n of cardinality k. So J is from Ja, then J plus 1 is from J. Well, this is I think. Well, let's do like this. I want
to exclude n from J.
Yeah, and then J from J is not n. I think this is correct. Okay. But then if J minus 1, I think you should exclude 1. So because the picture should be like, so maybe you are also right, but so the picture is that you have this J plus 1 and it's always defined, but if J is not n. So, well, maybe it's not that important, but so anyway, I think this is the picture. Maybe J minus 1 also would work.
I mean, subtracting 1 is you always take modulo n, so it's not really important.
Yes.
But I'm not sure
This looks, you see, it looks a bit more natural because
No, of course, plus is always better than minus, but if you want it.
okay, anyway, I hope this is correct. Now, okay. Good. So, and actually, this picture somehow resembles the example we had here, because here you see we are going somehow the number of vectors now changing. Well, okay. Good. So let me go to part 4. So the first of let me put the theorem, the first maybe part of the theorem, saying that xkn admits cellular decomposition so maybe let me repeat what I said last time, that is based on my joint work with Martino Lanini and Alex Putz. So xkn admits cellular decomposition such that these cells are in bijection with T-fixed points. So now this is the genuine cellular decomposition into affine cells. So, well, let me give you an example. N is 2 and K is 1. So we had it in a very explicit way. So you can see that these are 2 P1s. And then you know that So if you take this point where they intersect, then you can decompose each P1 as one-dimensional cell, and then this point, and then once again this one-dimensional cell. Okay, so this is this decomposition, and you see this agrees with the 3 Grassmann necklace we have. So the let us list all Grassmann necklaces. So they are of the form here. So if I take I1 and I2, so they are either 1, 1, 2, 2, or 1, 2. Yes, there are 3 of them. So either their 2 numbers are equal, so k is 1, so both of them consist of 1 number. And so if you have 1 here, you can have 2 here, and vice versa. And you see you have 3.
But it's not the
Thing.
It's not the T.
Yeah, it's very different because you see the CNN Grassmannian is not a complex algebraic variety. Yes. So this CNN Grassmannian is some combinatorial rather object, and the cellular decomposition for the CNN Grassmannian is a decomposition into real parts. Yes.
Oh, okay, yeah, okay.
But actually the point is that it's very similar. So in the following sense, I'll make it explicit right now.
Did Shin want to say something?
Yeah, I just maybe want to ask, so is this XKN equidimensional, and how many components?
Very, very good question. So I'll say in a minute. So actually, this is very nice about this variety that you can answer actually your questions. And so for GER KN, so we also have a cellular decomposition. But you see these cells here are greater than 0 to some power s. And actually this is what Zhenya last time complained about, that these are not really cells. You can't say that it's really Poincare polynomial. But here, so the claim is that the Euler characteristic of this algebraic variety, projective algebraic variety, is actually more or less the same as here. And moreover, the following theorem holds, which is more delicate but still true. So the Poincare polynomials of this totally non-negative Grassmannian and XKN are dual. So actually dual in a very explicit sense. So let me actually, So let me actually recall that here, maybe that GER 1, 2, or maybe put it here that GER 1, 2 is was. This is, so you have pairs AB, both being non-negative. So this decomposes as 1, 0, 0, 1, and 1B, where B is positive. So it means that you have point, and R. So you have 2 zero-dimensional cells and one one-dimensional cell. And here you have two one-dimensional guys and one zero-dimensional.
So you mean, for example, if I take x to 4, I will get 6 components, right?
If you take to 4, you have 6 components. Yeah, you are absolutely right. Yes.
Okay. Yeah. Thanks.
So you mean 6 irreducible components,
Yeah.
and each of the components being 4-dimensional.
Yeah.
So so let me actually maybe state it here. So here the theorem says that the Poincare polynomials are dual, so just changing the dimension. But let me actually say what Shin says here. Maybe I should have said it from the very beginning. The dimension of xkn is exactly the dimension of the Grassmannian is k times n minus k. So this is absolutely not evident, so that the dimension does not jump. So I'll say in a minute why one should somehow expect some connection to the Grassmannian, some link, but the claim is that the dimension is the same as for the Grassmannian, and also so the number of irreducible components of xkn is n choose k. So you see this somehow very funny that you have, so the dimensions are the same, and this number is exactly the number of t-fixed points in xkn, in Grassmannian. So it means that, so you have a variety which has the same dimension as the Grassmannian, but it's much more complicated, meaning that it has many irreducible components, and actually each component is top dimensional. Yes?
No.
So you see, it's very similar to what we have here. You have two components, both of them are one-dimensional, so as complex varieties. And this number 2 is actually the number of t-fixed points or characteristics of the Grassmannian one. So this is somehow a mixture, somehow a final mixture.
How do you say which fixed point is contained in which component? By the rest.
Yes, you can. You have to say that. So there is some order on Grassmann necklaces. So each component, each irreducible component, has top dimensional cell. So it's the closure of one cell, which is top dimension. And each cell corresponds to a t-fixed point. Yes, so first of all, what you have to say are what are the Grassmann necklaces corresponding to top dimensional cells. Yeah. So let me write it as a proposition. So there are Grassmann necklaces. So let us fix. So let I be an element in Nk. So just a k element subset of the set 1 to n, and then I can define IA to be just I for any. So I'm very naive. Yes. So and this is then the cells corresponding to the Grassmann necklace. R of dimension k times n. So, and then, so this is the description of the top dimensional cells, and these are all top dimensional cells. And then in order to answer Igor's question, you have to say what are the smaller cells in the closure of a given one. And for that, you have to introduce some order on Grassmann necklaces. I don't remember if I said something last time.
Well, we had some order. Is it the same?
Probably. So, I mean, there is an order coming from this shifted order on this. This is
Okay.
so then,
According to which the elements of a Grassmann necklace are the smallest. So to obtain a Grassmann necklace from a positron, you take the smallest with respect to different orders. And these are those orders.
say again?
You had, so then there was several orders. There was this order less than 8 on numbers from 1 to 9.
Yes.
You obtained an order on subset on K and
Yes.
subsets, and from that you obtained an order on
Grassmann.
several orders on
One order on Grassmann necklace.
several orders on K and subsets, and one order on
Absolutely. Absolutely.
And this is the same.
Yes.
order.
So for example, let me give you, oops. So there is a unique zero-dimensional cell corresponding to the smallest Grassmann necklace. Which is given by IA equals to A plus 1, so on up to A plus K minus. So A from 1 to. So there is a single zero-dimensional cell, and this zero-dimensional cell corresponds to this guy. Of course, here you have to understand this number is modulo n, but this is the smallest, and in this order, this is the smallest Grassmann necklace. And you can actually see that for totally non-negative Grassmannian, there is a single top-dimensional cell. And here, this is the smallest cell of dimensions. Okay. So what else can I say now? Yes, maybe a few words since my time is more or less over. So let's
start at 10 minutes.
Yeah, well, yes. So let me say a few more words about so about the last part. So why is it somehow useful to realize something as a quiver Grassmannian? So first of all, before that, yes, no, maybe let's include it in this part. So the first thing, why do we expect a link between the Grassmannian and XKN? And here is the reason. So let me consider a bit different representation. So let's say M be a delta n module of dimension n. So I take still the same quiver delta n, and then I take a module such that dimensions of all the spaces with all the vertices, they are the same, and the maps with all the maps being identities. So I just say that all these spaces are one space, and then the maps are identities, and then I can consider the quiver Grassmannian kk of this n. And this quiver Grassmannian is obviously isomorphic to the Grassmann variety. Yes, because so if I fix something at one vertex, then all other vertices are fixed. And now what I'm doing, I'm so keeping the dimensions of total space and of sub-representations. We are changing the maps. Yeah, so you remember that for our UN dimension is n. So the same as we have here, but the maps are somewhat different. So I mean, here these are all isomorphisms, but in our case we have co-rank 1 maps. So you might somehow be interested in the question what's happening when you are changing the dimensions, the ranks of the maps. And the claim here is that the dimension of this quiver Grassmannian does not change, although the variety is very different. So in particular, we see that it becomes highly reducible, but has still. So you see that some funny thing happens here, that you change some data, the ranks of the map, and then the dimension still the same, but the properties are similar to the totally non-negative Grassmannian, and it's absolutely unclear why this should be. So there's some observation, but
more like dual. But maybe after your
okay. So this is probably the first remark. The second remark is that there is a group which is so that G be the automorphism group of UN. So the automorphism of representation is actually a very simple thing. So you have M, and then there are Q modules. And then you can consider the maps from MA to NA, which commute with the maps in the representations. Yes, so here you have your G, your GA. So an automorphism is somehow a map from MA to NA for G. Such as it commutes with all the arrows, with all the maps, and then you can consider the automorphism of your representation. There is one observation that G acts on the quiver Grassmannian. Actually, on any quiver Grassmannian, particularly on our quiver Grassmannian, and then so this means that you somehow get the group action from the very beginning, and then you can ask what's the properties of this action, how you can study the structure of the variety, and in particular, here it turns out that all the cells are actually orbits of this automorphism group, and this is similar to what happens in the flag variety case. So, and maybe the last thing is that you can ask what are the properties of the irreducible components, and so the irreducible components are in general singular. And then there's a question how to desingularize, how to resolve the singularities. And actually, it turns out that the quiver representations, they help to do this. So, I mean, you can construct resolution of singularities in terms of quiver Grassmannians for some extended quiver, larger quiver. And this somehow allows to study the components in terms of quiver Grassmannians. So I think that's it. And for you, if you have any questions, please.
Клетки, которые соответствуют как Grassmannian движению, они примыкают соответственно порядку.
Да. Утверждение, что so the claim is that if one Grassmann necklace is smaller than the other, then the corresponding cell sits inside the closure of this larger. If and only. And actually,
В маленьком порядке изучать большое.
yes, so you're absolutely right. So in totally non-negative Grassmannians, the order is reversed. So it means that the small cell, the small Grassmann necklace, corresponds to a large cell. And here, this object somehow better compatible with these Grassmann necklaces. So in the sense that the smaller cell corresponds to the smaller Grassmann.
So when all elements are the same as the large cell, right?
Yes.
In the order.
In this,
Свойственность распространяется еще и на то, как они помогают.
Что, простите?
Ну, двойственность прямо вот.
Да. So you can say in the following sense, if you consider the pole set on these Grassmann necklaces coming from these closure relations, then the two pole sets, totally non-negative pole set, our pole set, they are zero.
So, but you don't know anything else about the geometry of the components.
In what sense?
So I don't know.
Not really. So the only thing we know is that there exists the resolution of singularities and we can construct it. But nothing more.
Have you tried like obtaining a projective realization of this, like in book recordings or something?
So you mean that it's embedded into the product of projective spaces, right? So because so by the very definition, it sits in the product of Grassmannians, and they sit inside the product of projective space.
No, but I meant something closer to the actual Grassmannian, so like a projective, not multi-projective, but projective realization of book recordings. Is that possible?
Yeah, but you see, there is a very natural embedding, yes. So by the very definition, this XKN sits inside the product of Grassmannians. So sits inside the product from A1 to N, Grassmannian KN. because of each vertex, you fix a k-dimensional subspace of an n-dimensional space. And then, of course, you can embed it into the product P of lambda k of Cn. And then ask for the kind of group relation there. I don't know the answer.
But so you do not know if it's a flat degeneration.
It's not.
It's not. Why? How do you know it's not?
Well, I mean, you can consider some small example in case 1 and 3 and compute the for this embedding, compute the multi-homogeneous
The
coordinate.
idea, and it's not an issue.
It's not the same. Not of the same size.
It's not the same size.
Yes, it's not the same. Which is a bit annoying, but it's not. So we have this example.
Well, technically, I'm thinking if this excludes it being a flat degeneration.
I'm not sure, but it's not. At least it's not a flat degeneration. It's very, in very concrete sense.
Okay. Of course, I was hoping.
Okay. Me too.
Okay. One more question.
Yeah.
Or Shin, do you have a question?
So I have maybe a stupid question. So is there a clear relation between xkn and xn minus kn?
Say it again, the xkn and the
xn minus kn.
You mean n minus kn?
Yes. Yeah. They have the same number of components. And I mean, as you explained in this section 5, this philosophy. So if you take the identity everywhere, then this is the same isomorphic. This is orthogonal, let's say.
Does
And
this preserve? Is the full set the same? The full set of Grassmann necklaces doesn't change.
I'm not. It's
Yes, I think it's dual. I think the full set is dual because you can take the complement.
what do you mean by dual?
No way, because you see, there should be one single.
Okay.
Yeah, because this is the.
Because you see, you can take the complement, so you have a k element set and the n minus k element set, and then here you're adding a.
So
yeah,
usually when you have a matroid, then you can consider the dual of the matroid. It's still a matroid. But I don't remember, is there such result on the positroid?
Yes, actually, I don't know, Shin, but I think should be some duality of probably of some similar way, similar sense what Igor is saying, but I'm not sure. So I don't know. But it's actually a good question, yeah. It's a good question. So you're right, one would like actually to take the complement, right?
The complement.
Yeah, it's natural to take the complement.
But the problem, what I don't understand, that indeed, if you take the complement to the zero-dimensional cell, you're getting something very different. So this is not.
The complement to the zero-dimensional cell. So there's one view from A to A plus k minus 1.
Yeah.
No, but why? It starts with A plus k and goes and minus, so it goes all the way around.
That's right.
K elements. So it's kind of shifted.
Yeah.
It's a shift. It's one. Yeah. Maybe.
I think you have to
Maybe shift back.
You take the complements and then you have to change the order of the elements and you have to rotate the necklace.
Maybe.
Yeah.
So maybe this should work in the geometric sense also, but
I think
I
you just have to reverse the net.
maybe
You have to reverse. the
maybe you have to reverse, maybe. Yeah, but I never checked it.
Yeah, you have to take the complement of some vector spaces.
In some,
Also, let's say orthogonal.
maybe in some sense.
The
Yeah.
complement of the set or the orthogonal dual
Mhm. Yeah, maybe.
of the vector space.
Yeah, it's a good question actually. But I never checked it.
And as long
Yeah, sure.
Thanks.
maybe I forgot, so last time you told us that in terms of these Lie diagrams, that the dimension of the cell is equal to the number of ones.
Absolutely.
But you did not say how the dimension is computed in terms of the Grassmann nexus, right?
I didn't.
So here,
This is the way. In some sense.
what is the way?
Well, I mean, how to say you're asking how do we prove or
Yeah, like for this or for the
yeah.
for the T-N Grassmannian, what is the dimension of the cell?
So you can't say it very explicitly,
Yes.
although you can say it in some way in terms of this action of the group. So since I said that the cells are the group orbits, so you just have to understand what's the dimension, how does this group acts on your T-fixed point.
Mhm.
So what's the dimension of the stabilizer? And there is a way combinatorial to say, but we did not somehow compute it explicitly, but rather we compare the posets. So we checked that, so somehow in the case of this variety, so you have the closure relation, and the closure relations are the same for total and negative Grassmannian and for this very variety. Yeah, and then you reverse absolutely. And then you check that there is one single zero-dimensional cell here and one top-dimensional cell here.
Well, so if one element covers another in the poset, then the dimension difference is necessarily one.
This has to be proven, but it's true in both cases.
Yes, it is true.
Yes, this is how it works, how the proof works.
No. And then you can sort of complete the length of the change,
Absolutely.
the height of the.
Absolutely.
Okay.
So any further questions? Okay, then.
I have a question. So for those listening online, can you hear me? So the question if they can hear us well in the audience, maybe you should ask them.
Yeah, so what we're interested in, can you hear the questions asked from the audience by the offline participants?
Yes, I can hear Igor.
You can hear. Okay.
Yeah, I'm gonna close this one.
Yeah.
To the microphone.
Okay, probably this, if you are sitting somewhere.
Can you hear them?
Что-то там едет у вас, да?
Значит, что-то слышно. Скоро помощь.
Okay, then thank you and bye bye.